in listen-only mode.
Okay, hello everyone. Good afternoon. Thank you so much for taking the time to attend our seminar. My name is Daryl. I'm just an engineer here at Midas, and before I begin, I just want to make a quick sound check just to make sure that everyone can hear me loud and clear. So if you could just use the menu for your GoToMeeting icon, just click on the hand raise button just to let me know that I can hear you. Okay, so I see just a majority of the hands are raised, which means I assume mostly everybody can hear me. If you're having any audio troubles, just send me a message through the chat box, and we'll just hold up and we'll fix the audio for you. Okay, so now let's just get started. As you can see, today's session, first off, will be on response spectrum analysis of conventional bridges. This will be the in-depth study session, and it will be led by Nitil Malguri, our senior bridge engineer. But before I begin, I just want to quickly go over the Midas e-learning courses, which is a program we'll be holding this month as well as next month, because I see a lot of new sort of attendees here, so I understand that maybe a lot of you aren't quite familiar with the e-learning courses yet. So first, let me just make this introduction, and then we'll get on way with the seminar. Okay, so what are Midas e-learning courses? So basically, they're just this technical service that we're providing just to give bridge engineers an opportunity to learn together. And these consist of a series of courses. So first, there will be a technical seminar given by one of our clients. Just the leading professional in his field will be discussing a certain design topic, followed by an in-depth case study and discussion, which is the course that you're attending right now, which will be on response spectrum analysis. And then finally, a third course will be given afterwards on numerical modeling and analysis training, which is specifically for applying what you have learned into a specific project. So as you can see, it's really important to understand sort of the process or the progression of these seminars. The foundation or the general application knowledge will be given here. And then as you go to courses 2 and 3, the information or the training will become much more specific. Okay, so why exactly are we hosting these courses? First and foremost, we just want to contribute to our clients, or we want to help our clients through our technical services, through the spreading of technology and knowledge. A lot of our clients, they're experts in their field. They have extensive knowledge on certain design topics that are of interest to many engineers just across the country. So we just find that it's a good way to receive free training and for engineers to network with each other. Also, we hope to spread our technology. Throughout these courses, you'll be learning how certain finite element analysis packages can be used specifically to help you work more efficiently with these design topics. And of course, to bring happiness to engineers and to lead to breakthrough. So we hope that these seminars will be of use to you, that you'll be able to apply them directly to your own projects, and that you'll be able to use this knowledge to work more efficiently, to work on bigger projects, and to better meet your goals. Okay, so the technical seminar. So as I discussed before, the technical seminar is just the general session where we introduce the design topic. And the technical seminar, the discussion will always be led by a professional engineer from one of our clients, usually from a leading design firm, but sometimes from a DOT or a local university. And they'll be discussing specific bridge projects that they are experts or specialists in. And of course, they'll be discussing certain challenges that are faced with this unique design topic, and they'll discuss how specifically to overcome them or what certain methods have worked best for them in the past. Okay, and the benefits of attending the technical seminar is first and foremost to receive first-hand information from one of the experts in the field. Once again, the clients or the speakers that we select, they're very specialized in their certain design methods or their design topics. So it's a good way to learn from an expert just firsthand, directly from their past project experience. And they'll be giving a technical overview of the design considerations. So usually what they'll do is they'll give one of their past projects as a sort of a case study, and they'll sort of allude to that and to sort of show you how certain challenges were faced and how they were able to overcome them. Okay, and also it's another good way to learn about certain landmark projects in North America. Oftentimes our speakers select projects that were very high profile or that received a lot of attention, and it's a good way to learn about the different sort of new projects that are being completed here in North America. And last but not least, it's a good way to network. Our speakers, they welcome questions, they welcome communication, so it's a good way to just expand your professional network and to gain the acquaintance of other engineers that are out in the field. Okay. As you can see, we have a wide range of speakers ranging from leaders in leading companies as well as DOTs and universities or professors from universities. Okay. So next, the in-depth case study and discussion. So once again, you're all enrolled in the in-depth case study for response spectrum analysis. So following the technical seminar by one of our clients, one of our bridge engineers, we'll give a detailed discussion on what was discussed previously. So for example, they'll take the general knowledge that was discussed and they'll relate it to a specific case study in either the US or Canada. And they'll also introduce the latest technologies of numerical modeling that are being used to handle these types of project applications. And then the benefits. So recently, finite element analysis has become more prevalent in bridge design because it's really the most sophisticated, it's the most efficient way to handle bridge analysis, especially for the high-end projects that we'll be discussing. So for those of you who maybe are only sort of vaguely acquainted with finite element analysis, this will be a good way to get a better introduction to it, to understand how specifically it can apply to your projects. And through introducing this technology, you'll explore different approaches for modeling and designing, and you'll also understand how to specifically use this technology in your own work and in your own project applications. Okay. And then finally, for the third section, we'll be going over numerical modeling and analysis training. So what's really important to understand about this session, or these sessions, is that you'll be taking, all of the knowledge and all of the skills that you learned in your past two seminars, and we'll be applying them specifically into a project application. So once again, they'll be giving step-by-step modeling techniques on how to design and analyze these bridges. They'll also sort of teach you how to read through the detailed results output to better meet the design checks for your codes that you have to meet. And the main benefits are to learn correct numerical modeling. For those of you who aren't maybe experienced with finite element analysis software, this is a good way to get into it and to get started with it. And also you can explore different concepts of different analyses. You can get updates on North American design codes. So we make sure to keep our clients and our attendees up to date with not only the newest updates in technology, but also in the design codes themselves. And also, this is very important, all attendees will receive free training software. For those of you who don't have any finite element analysis software, we are giving out free trial versions of Midas Civil so that you can try modeling your own projects onto the software, or you can try modeling the projects that we've discussed onto the software to see how specifically finite element analysis can really just sort of change how you do your projects and how you do your work processes. Okay, and here's just a quick screenshot of Midas Civil. It's a very advanced and sophisticated software. All of our speakers use it. They find that it helps them to work more efficiently to gain higher quality analysis results. And once again, all attendees of our technical training seminars will be able to receive a free trial version of Midas Civil so that you can use it for yourselves. Okay, so that about does it for the introduction. From this point on, I'll just let Nithil take over, and he'll present the second course, the in-depth case study of response spectrum analysis for conventional bridge types for you.
Thank you, Daryl. I'm Nithil from Microsoft, and I welcome you all to this in-depth analysis and case study for demand and capacity evaluation for the seismic design of a bridge. Before I start, I would like to make sure that you guys can hear me properly. So if you guys can hear me, please let me know through the chat window, or you can also raise your hands. So if there is no problem in the audio, please let me know through either the chat window or you can raise your hands. Okay, perfect. So I guess everybody can listen to me and you guys can see my screen. So as Daryl has just told you, today we are going to do an in-depth analysis, and we are going to talk about a case so that we can perform the seismic design of a bridge using the AASHTO guide specification for LRFD bridge design. For performing this type of seismic design check, I have chosen a 3-span continuous conventional steel I-girder bridge, and we would perform the response spectrum analysis to obtain the demand, and we will perform the pushover analysis to obtain the capacity for in case of a seismic event for this particular bridge. I will talk about the details of this bridge later, but before I talk about the details of the bridge, I would like to do a recapitulation of what was discussed by engineer Ling Zhao of Michael Baker regarding this topic. So for those of you who were present in the technical seminar done by Ling Zhao from Michael Baker, he talked about the difference of approach between the force-based design and the displacement-based design, and he told you that now the seismic design is moving towards displacement-based design from the force-based design. And he talked about the different concepts of response spectrum analysis and pushover analysis and what are the different codal provisions for those type of analysis. So before I would like to start my case, I would like to do a brief recapitulation of what was discussed in that seminar. So first of all, Ling Zhao talked about the force-based design, and this is an exact slide that I've taken from his presentation. And here you can see the basic concept of force-based design. If in the event of an earthquake, the force applied is F and the structure behaves elastically, I mean we assume that the structure is behaving elastic, then it will have a linear relationship with the force applied. So basically whatever force the earthquake we are applying in the form of an earthquake, there would be a corresponding deformation or forces or stresses generated inside the structure based on the force applied, and they will have a linear relationship. But in actual case, the structure will not have an elastic response throughout the earthquake. It can have failure of certain elements, and certain elements can go into inelastic range. So this is how the actual response of the structure is obtained. So you can see the difference between the elastic analysis and the inelastic response, and this is I mean, when you talk about the inelastic response, the design load will be reduced by a factor R, which is written here, and it would be nothing. I mean, if you see this, these two similar triangles, the one for the elastic analysis and one for the, I mean, till the point the elastic analysis changes into inelastic analysis, you can basically, you know, take into account these two similar triangles, and you can obtain that the design force for the earthquake would be reduced by a factor R. So this is the approach for the force-based design. We obtain the force generated by the earthquake, we obtain the effect of that force on the bridge, and then we design the structure accordingly. And the ratio of the inelastic and elastic response divided by the elastic response will represent the ductility of the bridge. Now when we talk about the displacement-based design, the displacement-based design is actually based on the full inelastic response of the bridge, and here we try to compare the demand based on the displacement and the capacity of the structure, and a simple check is performed that the capacity of the structure must be greater than the demand. So the demand is obtained by an earthquake, and the capacity of the structure is obtained by performing inelastic analysis and defining several factors which are included so that we can take into account the inelastic behavior of the structure. So today we are going to talk about displacement-based design, and for doing the displacement-based design, as I mentioned, we are going to follow the AASHTO guide specification for LRFD bridge design. So let me simply do a comparison between the force-based design and displacement-based design, and again this is a slide taken from Ling Zhao's presentation, and here you can see the vital differences between the force-based design and displacement-based design. You can see the important differences I have marked in red color, and in the force-based design the elastic demand forces are divided by the response modification factor, or as I discussed just before, and in the displacement-based design the displacement demands are checked against the displacement capacity. So whatever displacement demand that you obtain from the earthquake, from the applied force due to the earthquake, you check it against the displacement capacity. In the force-based design, you check the ductile response is assumed to be adequate without verification. We just assume that, you know, the ductile response will be adequate in the event of an earthquake. But in the displacement-based design, the ductile response is assured with the limitation prescribed for each STC. Basically, in the AASHTO LRFD seismic design code, we have 4 STC, STC A, B, C, and D, and the ductile response for all these four STCs are written in the code, and you have to follow these specifications of the code. And today we are going to talk about briefly about these STCs too. And finally, in the force-based design, the capacity protection is assumed, while in the displacement-based design, the capacity protection is assured. So these are the major differences between the force-based design and the displacement-based design. And when we talk about the displacement-based design, we have to, perform the capacity check for pier, column, foundation, joint, whatever elements that are present inside the bridge structure. So before I start calculation of demand in the event of an earthquake, I would like to take you to Midas Civil itself, and let me give you a brief idea about the type of bridge that I'm going to demonstrate for the calculation of demand. Okay, so on your screen now, you guys can see Midas Civil. So on your screen now you guys can see Midas Civil, and in Midas Civil I have modeled this particular bridge. You can see that this is a conventional highway bridge, and it's a 3-span continuous structure, and I have modeled the different stages of construction of this particular bridge. So let me show you the stages of construction that I have modeled in Midas Civil. So first stage, the erection of pier has been shown. In second stage, the steel girders have been installed along with the 3D cross frames. So you can see the cross frames here along with the steel girders. And in this particular stage, the scaffolding has been applied and the wet concrete has been poured. And in the third stage, the structure becomes continuous and the deck concrete becomes continuous with the steel girders. So this is how I have modeled 3 different stages of construction of this particular bridge. Although if there are several other erection stages included, we can model that in Midas Civil. But more or less, this is how I have modeled the bridge in Midas Civil. And again, it's a composite structure. It's a steel composite bridge, and it's a 3-span continuous structure. So this is the bridge that I'm going to talk about throughout my webinar today, throughout my discussion today. And so let us now begin with the demand analysis for this particular case. I'll go back to my presentation now, and let us see what the code says about the different STCs as we discussed before, and how the seismic design of these different classes will be done. So here, when we talk about STC A, there are no such critical seismic design parameters which are included, but when we talk about STC B, C, and D, which are more critical, I have shown you the flow chart of performing the seismic design check as per the AASHTO LRFD seismic design code. And here you can see how you will go about performing the design check for STC B, C, and D. And D is the most critical case. It is the most complex case, and that's why I have chosen STC D. And this flowchart has been taken again from the AASHTO LRFD seismic design code. So all the symbols and everything that you see here, the figures that are mentioned in this particular picture, are all taken from AASHTO LRFD seismic design code. So here it says that when you are performing the seismic design for a STC D type of structure, you have to first perform the displacement demand analysis, then you will perform the displacement capacity analysis, and then you will check whether the capacity is greater than the demand or not. So this is how you will perform the seismic design check for an STC D type of structure. And after you satisfy the design criteria, then you will perform the capacity design, the foundation design, and finally you will perform the detailing for the drawings. So first of all, let us begin with the demand analysis for this particular bridge. So as on the right hand side, you can see the flow of this particular seismic design check for this particular bridge. And here I have marked out the box, where we are. So first of all, we will do the displacement demand analysis. So in the displacement demand analysis for STC B, C, or D, they are all same. You have to first do the seismic design proportioning from the recommendations which are proposed in the code. So let me talk about some recommendations which I think are important. So the first recommendation or the consideration that the engineer should do is mentioned here, and we should check whether the stiffness with variable and constant frames are according to this clause of the code. And the second consideration is the periods that are obtained after performing eigenvalue analysis. The ratio of fundamental periods of vibration for adjacent frames in the longitudinal and the transverse direction should satisfy this clause. So these are the two important clauses that are there in the seismic design code, and when you start obtaining the demand as per the design code, maybe you have to take care of these two considerations, these two special considerations from the code. After that, you can go ahead and perform the displacement analysis, and again these pictures and everything has been taken from the seismic design code. Here you can see for seismic design category A, for regular bridges the demand analysis is not required, and again for not regular bridges with two or more than two spans it is again not required. So that's why I've chosen SDCT. And here you can see that for B, C and D you can use either procedure 1 or 2 for obtaining the demand. So here we have a procedure number and the name written. The procedure 1 is equivalent seismic analysis. So here what we can do is we can apply the earthquake load in the lateral direction as an equivalent static load, and we can obtain what is the demand. In the second procedure, you can perform an elastic dynamic analysis, which is nothing but a response spectrum analysis. And the third procedure is performing the nonlinear time tree analysis to obtain the demand. In previous sessions that were conducted by Parsons Brinckerhoff, Ben from Parsons Brinckerhoff talked about how to perform the nonlinear time tree analysis to obtain the demand. And in the follow-up session, Puya from our office, he talked about how to perform the nonlinear time tree analysis in Midas Civil and obtain the demand. So today we are restricting ourselves to response spectrum analysis and this conventional structures. For the conventional type of structures, response spectrum analysis is more than enough so that we can obtain the demand. So let us begin with the elastic dynamic analysis so that we can obtain the demand for the structure. First of all, I would like to highlight some of the considerations from the code, especially section 5.4.3 talks about different considerations that you have to take into account while performing the elastic dynamic analysis. So the first consideration is at least 90% mass participation in longitudinal and transverse direction must be taken into account while performing response spectrum analysis or elastic dynamic analysis. The damping that we should consider for performing the elastic dynamic analysis should be 5%. And for elastic dynamic analysis, most results must be combined by CQC method, or which is complete quadratic combination method. So I'm going to talk about what these mass participation means, damping, you guys all know what damping is, and how do we combine the results using the CQC method. First of all, let us go into the theory of elastic dynamic analysis and see what are the factors that influence the results of elastic dynamic analysis. So first of all, before performing the elastic dynamic analysis or response spectrum analysis, you need a response spectra. You need a response spectra for a particular site, and Ling Zhao in his session he talked about a website from where you can obtain the response spectra. The response spectra is important because all the loading that you will apply to your structure will depend on the response spectra. Second factor that will affect the elastic dynamic analysis is the behavior of the structure. So as I mentioned, while you are performing the elastic dynamic analysis, you will always consider the structure to be in elastic limit and it will be damped, and the foundation behavior will be considered linear, that is, it would be elastically linear while you are performing the elastic dynamic analysis, and hence the name elastic dynamic analysis. So talking about these factors one by one, let us see how the response spectra affect the results from after performing the elastic dynamic analysis. So here you can see I have a table in which I have written the mode number, the frequency, and the period for a particular structure, and the equation, the equation of motion which will govern the results of response spectrum analysis. Here you can see that the mass of the structure, the mass matrix multiplied by the acceleration, the damping multiplied by the velocity, and stiffness multiplied by the deformation will be equal to the mass matrix multiplied by the acceleration. Now this acceleration will be obtained from the response spectra. So here you can see that the different modes are listed, the frequency is listed, the period is listed. So if you talk about mode 1, the acceleration will be taken from the response spectra in this fashion. So for the mode 1, the period is 2.41 seconds. So the acceleration would be 0.75 multiplied by the acceleration due to gravity, which is 9.8 meter per second square. And you can take this acceleration and then apply onto this equation, and you will obtain the effect in mode 1. Similarly, you will do the same drill for mode 2. You will obtain the period for mode 2, and based on that period, which is 1 second here, you will obtain the acceleration from the response spectra. So if the response spectra gives you more acceleration, the effect will be higher. So the response spectra will affect the analysis results from elastic dynamic analysis. Now, talking about the second factor, as I've already told you, the structure is supposed to behave linearly elastic in elastic dynamic analysis, and the damping will be considered as 5%. And talking about the foundation, as you know, the bridge will have a foundation which will go into the soil. It can be a piled foundation. And when you talk about the soil, it has a certain load versus displacement graph. So here I have shown you a load versus displacement graph, and you can see as you keep on increasing the load, this is a lateral load to the soil, it will have a certain displacement, and once you keep on adding the load, keep on applying the lateral load, keep on increasing it, it will go into non-linear location. So as you can see here, for performing the elastic dynamic analysis, you have to take into account the elastic linear behavior of the foundation. So we will idealize the stiffness of the soil. So the black line here, it represents the idealized stiffness, and we are going to use the idealized stiffness for performing the elastic dynamic analysis. So let us now talk about the different steps that you have to follow for performing elastic dynamic analysis, and these are the general steps that you will follow for performing elastic dynamic analysis. It has nothing to do with any finite element analysis software, be it Midas Civil or any other software. These are the general steps that you will follow. So once you are done with doing the modeling or creating the mass matrix of the bridge, the step 1 will be the generation of response spectra. As to LRFD, it has certain guidelines, and you can create the response spectra based on the specifications given in the code. And this is a diagram that I've taken from the code itself, and it shows you the values at different location for the response spectra. You can obtain the values here, and the code has different maps, and you can obtain the values of PGA, which is the peak horizontal ground acceleration coefficient, and you can obtain STS and ST1 based on these equations here, and then you can create your own response spectra. But as Ling Zhao mentioned in this presentation, that you don't have to use these equations always. Now we have a website which can automatically create the response spectra based on the coordinates that you specify for your bridge. Now let us talk about how you can obtain the response spectra in Midas Civil. Basically, when you talk about a finite element analysis software, they have certain built-in codes and database which will help you to generate the response spectra based on the code automatically. So now let me show you how you can use Midas Civil to automatically specify the response spectra. So let me switch to Midas Civil itself, and let me show you how you can do this kind of definition in Midas Civil. So I'll go to load, and I'll go to seismic load, and I'll go to response spectrum functions. I'll click on add here, and you can see that there is a button for design spectra. And here you can specify what is the site class. So as you know, code specifies A through E 5 different site classes. You can click on any of the site class. You can specify what is PGA, the spectral acceleration coefficient at a small interval and long period. And then you can specify what is the response modification factor. And once you click on OK, you can see that the response design spectra will be automatically generated by the program. So this is how you can create the response spectra, design spectra in Midas Civil, and I hope it is very convenient to do it this way. So you have two options. Either you can create it from the code, or you can use the built-in feature of any finite element analysis software to define the design spectra by yourself. Okay, so now we have defined the design spectra for performing the elastic dynamic analysis. Now let us move ahead and see the second consideration from the code. So as I said, the code specifies that you have to take into account more than 90% mass. More than 90% of the mass should be excited for performing elastic dynamic analysis. So I did a preliminary analysis on the bridge that you are working with, and I performed the eigenvalue analysis for 20 modes, and I realized that the mass participation factor for 20 modes was coming out to be almost 82.5%, and in the Y direction it was coming out to be 89%, which is not good. The mass participation factor is not good because it is less than 90%. So I increased the number of modes for this particular bridge. I increased the mode from 20 to 50, and you can see that the mode participation factor comes out to be more than 90% in the X and the Y direction, which implies that okay, now with 50 modes I can go ahead and I can perform the elastic dynamic analysis to obtain the demand due to earthquake. So this is how you will make a check on how the mass participation is obtained. It's very simple to do it in Midas Civil. Let me show it to you how you can do it. Okay, so again I am in Midas Civil, and for performing the eigenvalue analysis to obtain the mass participation factor, I'm going to go to analysis, and I'm going to go to eigenvalue analysis, and here you can specify the number of frequencies, the number of modes, and once you perform analysis, which will take about 10 seconds, you can go to mode shapes, and you can obtain the mode participation factor. So here I obtained the table for the mode shapes, and here you can see that for 50 modes you have more than 90% excitation of the mass. So you can go ahead and perform elastic dynamic analysis. Now let me show you the different modes for this particular bridge. So here I have different modes for this bridge. You can see different modes. If you want to see so this is the major mode in X, we have the major mode in Y, we have the twisting modes, etc. So this is how you can obtain the results for mode, and you can manually verify that okay, everything is working fine. And after you obtain these results for eigenvalue analysis, either you can perform the response spectrum analysis automatically, or you can take the periods and do a manual check for performing the response spectrum analysis. Okay, so before performing the elastic dynamic analysis, there are certain other conditions that you have to meet as per the code. Basically, the section properties must be considered as cracked. Basically, when you talk about the piers and all, they will have, they will crack because they will move laterally. So you have to reduce the stiffness of these members by some value before you perform the elastic dynamic analysis. So in Midas Civil, I applied certain stiffness reduction factors to the pier members so that I can take into account this clause. And after I performed the response spectrum analysis or elastic dynamic analysis, I obtained the demand in terms of deflection. So here you can see that the elastic dynamic results for response spectrum in X direction, it comes out to be 2.91 inches. So this is the demand which is obtained after applying the earthquake force. So the event of the earthquake, as per the criteria defined by the AASHTO LRFD seismic design code, the maximum deflection comes out to be 2.91 inches. And in the Y direction, it comes out to be 2.94 inches. Now let me take you to Midas Civil itself and let us see some other results which we have obtained after performing response spectrum analysis. Okay, so I'm switching from presentation to Midas Civil, and then I'm going to show you how the deformations look like. Okay, so now on your screen you can see how the deformation of the bridge looks like in the X direction after performing the elastic dynamic analysis or response spectrum analysis. And if you want to see in the Y direction, you can change the load case combination to RSY, and then you can obtain the same thing in the Y direction. You can also obtain several forces if you want to obtain the bending moment diagrams, the forces which are obtained in the different elements. You can obtain that. This is how the bending moment is obtained in the piers, in the event of earthquake in the X direction, and in the Y direction it comes out to be this. It's an exaggerated deformation, so don't worry about it, and this is how it looks like. So basically, after performing the elastic dynamic analysis, you can obtain the demand from the earthquake. So in the event of an earthquake, you can obtain the demand. And the deformations that you have just seen, they are all relative, they are not absolute. If you want to obtain the absolute deformation, you can just check off the scale of deformation, and then you can obtain the absolute deformations. So this is how you can obtain the demand after performing the elastic dynamic analysis. And for this particular bridge, the case that I'm presenting in before you, in the X direction, the demand comes out to be 2.91 inches, and in the Y direction it comes out to be 2.94 inches. Now if you go further into the code, you will realize that the foundation flexibility effect must be taken into account if the foundation is flexible enough. So what I did was I went into the drawings of the bridge again, I checked out the foundation of this particular bridge, and I realized that okay, the foundation flexibility effect must be taken into account while obtaining the demand for this particular bridge. So here you can see this is a picture taken from the code itself. The section 4.8 talks about it, and here you can see how the demand will change in the event of an earthquake for the flexible foundation. Now, right now these days we have a very high supercomputers which can perform, you have fast computers which can perform these kind of analysis in no time. So we can think about modeling the foundation and obtain the demand in terms of an earthquake. So basically what you are doing is, after you model the foundation, you can take into account the soil structure interaction in the event of an earthquake. So what I did was I modified the model so that I can take into account the effect of foundation. So now let me show it to you. Let me go back to Midas Civil itself, and let me show you how I perform the elastic dynamic analysis after defining the session. So here it is. Let me share the screen with you guys. So here you can see how the foundation has been modeled for this particular bridge. You can see the pile cap has been modeled, the several piles have been modeled. And the good thing about Midas Civil in this respect is that when you go to the boundary definition, we have a feature called as integral bridge support, and here you can just specify the soil support, and you can define the pile springs automatically in the program. So basically you need to punch in what is the ground level, the pile diameter, the unit weight of soil, etc. And Midas Civil will automatically generate the soil supports for you. And that is how I generated the soil supports for this particular bridge. Now when I perform the elastic dynamic analysis, I can obtain the effect of foundation in it. I can directly apply the earthquake onto a structure in which I can perform the soil structure interaction. And now let us obtain the deformation in this particular case. Okay, so again I will select the response spectrum in X direction, and this is how it looks like, and in Y direction this is how it looks like. And let us do a comparison on how the demand changes with the inclusion of foundation. So I did a simple comparison between the two models, and here I realized that the maximum deflection in the event of an earthquake when the foundation is considered, it comes out to be 5.92 inches, which is about 3 inches more than the case when we consider the foundation to be rigid. So it changes drastically. And again in the Y direction, from 2.1 inches it changes to about 5 inches, again a 3-inch increase. So basically, since the foundation is flexible enough, it will have a certain rotation in the event of an earthquake, and this will increase the demand for the structure. I am receiving a lot of questions from people, but what I'll do is I'll just complete the session, and after the session I'm gonna answer all of your queries. So here I have told you that the foundation flexibility must be taken into account while you are obtaining the demand for a particular bridge, and you have different softwares for performing finite element analysis, and the one that I used was Midas Civil, so I found it to be okay. You can perform soil structure interaction and you can obtain the effect of foundation in the event of an earthquake. So there is one more clause that you can follow for performing the seismic design of the bridge, and it is known as the 130 rule. I know many of you must have heard about it. Basically, it is taken from the section 4.4 of the code, and it says that when you are obtaining the seismic demand displacement along any of the principal axes, you can take the 30% from the displacement that you obtained after performing the elastic dynamic analysis in a transverse direction. So it means that you will take the 100% of the displacement from after performing the elastic dynamic analysis in X direction, and you will add to it 30% of what you have obtained after performing the elastic dynamic analysis in the Y direction. So basically you have to add 30% of the displacement obtained from the elastic dynamic analysis in the transverse direction. So this is the 130 rule, and it's very easy to do it in Midas Civil. You can create a load combination in which you can apply a factor of 1 to response spectrum analysis in the X direction and 0.3 to the response spectrum analysis in Y direction, and you can obtain the effect. So that is all about the demand analysis. Now we have obtained the demand for this particular bridge, the case that I have presented to you, and now we will talk about the capacity and how to obtain the capacity for an SDCD type of structure. So right now we are at the demand displacement capacity. First of all, I would like to talk about the factors affecting the demand, the determination of capacity. So we are going to perform pushover analysis for it as recommended by the code, and here we have to consider the nonlinear behavior of the material. As I mentioned earlier, that when you are performing the pushover analysis to obtain the capacity, you take into account the nonlinear behavior of the material. So basically the inelastic behavior of all the elements that are present inside the structure will be taken into account. There are different type of load application that you can apply in pushover analysis. There is a lot of research going on around on how to perform pushover analysis. I'm going to talk about the latest developments in this field also. And then you can you have to take into account the non-linear foundation behavior. As I've told you earlier, that the behavior of the foundation is non-linear. You have to take it into account while you are obtaining the capacity of the structure. Now let us talk about the factors affecting the pushover analysis in detail. So first of all, as I said, you have to take into account the non-linear behavior of material. As we know that after a certain range, the reinforced concrete or the pre-stressed concrete elements that we have in the bridge, they start to collapse, they create a plastic hinge, etc. in the model. So in the real case, when you apply lateral load, the piers will experience the highest bending moment, and they are prone to the development of plastic hinges, and the plastic hinge can either be created at the bottom of the hinge or at the top of the hinge. So this is how I have categorized the difference between the two types of members for the definition of plastic hinge. When you are talking about the flexural members, the one who transfer the load in flexure, the moment curvature is defined. But when you talk about the compression members, the PM interaction curve must be defined so that you can take into account the nonlinear behavior. So this is how you will do it. For flexural members, you can define the moment curvature, and for compression members, the PM interaction curve can be defined. Secondly, the type of load application can affect the capacity determination from pushover analysis, and there are different types of load application methods. I have chosen the two which are most famous. The first one is uniform acceleration. In uniform acceleration, what you do is you apply the load and you keep on increasing it by a certain rate. So here you can see I have 4 different masses. You can consider it to be a pier where the masses are lumped at different nodes, and I keep on increasing the acceleration and I will obtain the pushover curve. The second method could be the mode-shaped based, and here you apply the load on different masses based on the mode shape. So these are 2 different type of load application that are generally used for performing pushover analysis, and most commonly, almost in the 90% of the cases, you guys must be using the uniform acceleration method. You will keep on pushing the structure so that it obtains the nonlinear behavior, and then you create the capacity curves, etc. for performing the seismic design. The nonlinear foundation behavior should be taken into account. So this is the load versus displacement curve for the soil, and here you can see that after a certain load, the soil will yield, and this is how the PY curve looks like. And while performing the pushover analysis, this exact behavior, the exact stiffness of the soil must be taken into account. Now let us talk about the code considerations for obtaining the capacity. For SDC, B, C, and D, they shall satisfy this rule. As I said in the beginning, that is, the demand must be less than the capacity. For structure type SDC, B, and C, the code has certain equations, empirical equations, from where you can obtain the capacity. You can see how the empirical equations have been listed in the code. They are listed in section 4.8.2, and basically what you can do is for SDC, B, and C, you can perform the demand analysis, you can perform response spectrum analysis to obtain the demand, and then you can obtain the capacity from these empirical equations and you can compare. But when it comes to SDCD, the case we are talking about right now, we have to use a nonlinear static procedure as defined in the section 4.8.2 of the code. And this procedure again is known as pushover analysis, and we will perform pushover analysis on the said bridge, the one we are working on, to obtain the capacity. There are certain small things, certain considerations of the code that you have to take into account while setting up a pushover model, and one of the most important of them is listed in section 4.11.6, and it talks about the length of plastic hinge. Basically, if you are using the length of the element to be very long, it would give you a real nonlinear behavior of the pier, because it might have plastic hinges at the top and the bottom only, and it might never create a plastic hinge in the middle. So basically the length of plastic hinge, it has been defined by the code, it has been provided by the code, and when you are creating the bridge model, you have to take into account how to consider this clause appropriately. And the step 2 would be consideration of PM interaction curve in hinge determination. And the PM interaction curve can be defined while performing the pushover analysis, or if you are performing pushover analysis by hand calculations. At each step you have to see whether the P obtained from the self-weight of the structure and the moment obtained from the self-weight and the earthquake loading should not go beyond the PM interaction curve that you will generate for your cross section. So I performed the pushover analysis in Midas Civil again. I considered the several provisions of the code and I obtained the capacity curves like this. So here it shows me the capacity curve and it shows you the resultant base shear versus the displacement, and here you will see that it is perfectly linear till 5 inches displacement, and once it goes beyond 5 inches it starts to yield, several members start to yield, and you obtain the nonlinear behavior. So this is how the capacity curve is obtained. Now let me go to Midas Civil itself and let me show you how the capacity curves are obtained from Midas Civil. Okay, so right now we are at Midas Civil, and for obtaining the results of pushover, you can go to the pushover tab here, and let me show you how I have done the definition of different items. So as I said, you can define the pushover hinge properties. I have defined the pushover hinge properties for the pier, and this is how I have defined the pushover hinge properties. And in Midas Civil, we have a special consideration of the code which talks about the hinge length, and basically you can divide the element into different sections for defining the hinge. And I have divided the element into 3 different sections so that the hinge can be defined at 3 locations inside an element, at the rear end, the first end, and the middle, and it takes into account what would be the hinge length. Now I have taken into account the PM interaction curve because we are talking about a compression member here. We are talking about the pier, which is a compression member, and this is how the PM interaction curve is generated. Well, Midas Civil, it can automatically generate the PM interaction curve as per the H2 RRFD code, and let me show it to you how it looks like. Okay, so this is how it looks like. You define the reinforcement in the pier element and then you obtain the PM interaction curve like this. So basically if the load goes beyond this PM interaction curve, the hinge will be generated. Okay, let us see the deformation due to pushover analysis. So I'm going to go to results, pushover results. I'm going to go to deformations, and here let us see the deformation in X direction for pushover. Let me check off the value here. Okay, and you can move ahead and you can see how the value changes. You can also see the status of the hinge, whether it is under the elastic range or the nonlinear inelastic range. So let me show you how the hinge are formed. So if it is in, as you can see here, if the pier color is blue, it means that it is under the elastic range. The hinge has not formed yet. Now I changed the step from 1 to 7. The hinge is not formed, and now you can see at the bottom the hinges are formed. Again, you can see how the progression of hinges takes place, and this is how it is obtained. So basically you can obtain how the the hinges are yielding, and based on that you can obtain the pushover curve. It shows you the base shear versus displacement, and you can see the linear as well as the non-linear part in the X and the Y direction. Okay, so in this particular model you guys must be wondering that I didn't take into account the foundation, but Yes, we can do that. So let me open the model in which I have taken into account the foundation as well for performing the capacity analysis in Midas Civil. Okay, so here it is. Let me share the model with you guys. And here you can see that the foundation has been modeled, and I have taken into account the non-linear stiffness of the soil. So let me show it to you how I defined it. I used the multilinear support type feature in Midas Civil, and here you can define how the stiffness of the soil will change in the lateral direction with the application of the force. So here I have generated the PY curves for the soil, and it shows you that at 130 kips the yielding will take place, and then it will have, you know, almost, I mean, it will have a very low stiffness beyond that. So this is how I have defined the stiffness for the soil in Midas Civil, and now let us obtain the pushover curve for the same. So I'll go to pushover, I'll obtain the pushover curve, and now you will see that the structure in a way behaves better when you take into account the foundation, because as I said, the foundation itself is flexible, so there would not be a rigid connection at the base of the pier with the foundation, and the structure, you know, the hinges will be formed later. So you keep on adding the forces. If you compare this particular model with the model that I have shown you just now without the consideration of foundation, you will realize that the pushover curve that you obtain from this model in which the foundation is considered, the structure obtains a nonlinear behavior after much higher, you know, forces, at much higher forces, and you can say much higher deformation. So this is how you obtain the capacity after performing the pushover analysis, and then you can compare the capacity with the demand, and you have done the seismic design check as per the AASHTO LRFD code. Okay, so now let us talk about the, you know, the spin-off of response spectrum analysis and pushover analysis and the recent developments. So in this particular case, what I did was I checked what will be the effect of P delta analysis if I take into account P delta analysis in the demand calculation, and this is a comparison sheet that I have obtained, and here you can see that if I take into account the P delta analysis, the moment that I obtained will be on the higher side. So, you know, sometimes you have to take into account the P delta analysis, and Midas Civil does provide you with this feature. You can perform a P delta analysis while considering the response spectrum analysis. And again, I checked the deformation, and you can see that the deformation with the P delta analysis, it's a little on the higher side. So basically, when you are taking into account the P delta effect, the demand will be on a higher side. Okay, so now let us talk about the recent developments in pushover analysis. Basically, it's, you know, it's since earthquake analysis, seismic analysis are very hot topics these days, and you know, we are supposed to do these kind of analysis for all bridge types. So basically, I thought that I should tell you about the new developments, the latest developments that are being done in pushover analysis. So the first one is modal pushover analysis. The pushover analysis that I have just done for the bridge, it's a single mode pushover analysis. What I did was I kept on applying the force in the X and the Y direction, and incremental force is applied in the X or the Y direction, and I obtained the capacity curve. But when an earthquake occurs, in the event of an earthquake, the structure will vibrate in many modes at the same time. So it is evident that we should do the modal pushover analysis in different directions at the same time. And here I have compared a structure. You can consider it to be a pier, and I have lumped the masses here, and you can see the shape of the pier in mode 1, mode 2, and mode 3. And you can obtain the displacement capacity curve in mode 1, mode 2, and mode 3. And then you can combine them together to obtain the capacity, and then you can compare it with the demand. So this is one aspect of pushover analysis. You can perform pushover analysis in different modes, and then you can combine them together to obtain the capacity. But a more recent development in the field of pushover analysis is known as incremental response spectrum analysis, because let me tell you the underlying principle between incremental response spectrum analysis. In single mode analysis, as I mentioned, we perform the pushover analysis only in one mode. So since the structure will vibrate in many modes at the same time, this might not be the right approach. In the modal pushover analysis, we consider that one mode is independent of the other, but it is not generally the case. So the solution to these problems are incremental response spectrum analysis, in which what we do is for each increment loading, we perform response spectrum analysis and then we obtain the deformation. So basically, in different steps of pushover analysis, we will perform response spectrum analysis to obtain the effect. So these are the developments which are being done for pushover analysis, and I hope when you guys are designing structures, some codes talk about it, some codes do not talk about it, but these are the recent developments. So this is the case that I wanted to present today. If you guys have any questions, now you can type in your questions, and I'll try to answer your questions. Okay, I have on the screen now we have the email address of our technical support. You can send us the technical support at ts@midasuser.com. Your feedback and comments can be, we will be able to reply. So now we have, now let me answer several questions that have been asked by many people here. The first question is asked by Fabio. The question is the deflection absolute or relative? So as I mentioned while I was showing you the results, the deflections are not absolute, they are relative. But if you want to obtain the absolute deformation, you can also obtain the absolute deformation. Now the second question by Benjamin is how is the foundation model? Now the foundation has two parts in it. There is a pile cap which has been modeled using the plate elements in Midas Civil, and then the piles have been modeled as a beam element. And so first you have to model the structure part of it, then you can apply the soil support, and you can this is how you model the foundation. We do have separate tutorials, we'll talk about it, so you can dwell into those. Okay, there is one more follow-up question by Benjamin. The question is, what would happen to the model if the super sub isolators are used? So if the isolators are used, the behavior of the bridge would be much better, because then the load will not be transferred directly from the deck, which is the heaviest part of the bridge, to the pier. So basically the isolator, it will isolate the deck movement from the pier movement, and the structure will behave better. In Midas Civil, you can do this kind of analysis. You can define different type of bearings. Lead rubber bearings can be defined, which have the nonlinear properties. You can define the nonlinear properties, and you can take into account how the isolator will behave. Okay, now there is one more question by Mr. Wexler. The question is, can you use p-wise spring curves for piles in response spectrum analysis? Well, when we talk about the response spectrum analysis, generally the linear stiffness of the soil is considered. So the Midas Civil only considered the linear stiffness. The non-linear stiffness is not considered in response spectrum analysis. There is a question by Fabio. The question is, we can use STCC formulas too. Yes, when you are, if you don't want to perform pushover analysis, then you can also use STCC formulas for STCD, but it is recommended that you perform pushover analysis. There is a question by Kevin. The question is, are you in the AASHTO LRFD bridge design specifications? No, I'm not. Then there is one more follow-up question by Fabio. Does the code allow to use point of fixity instead of the model the foundation? Well, the code says that you can, but you can do that, but then you will have to apply certain empirical equations, certain empirical formulas to obtain what will be the effect of the flexibility of the foundation. There is a question by Angad. The question is how you can include the mass and stiffness of the barriers. You can consider the mass and stiffness of the barriers. All you got to do is define the masses at the location of the barriers. So that is general for any finite element analysis software. But if you are using Midas Civil, you can define the barrier loading, and you can convert the load into mass in Midas Civil. Midas Civil does have a feature by which you can convert the load of the barrier into the mass. So you can do that in Midas Civil. Okay, there is a question by Grant Fraser. The question is, what is the basis of built-in soil properties used in integral support menu? Basically, they are based on the RESI approach, and I forgot the name of this guy. Give me a minute here, and then I'm going to show you how the supports are generated in Midas Civil after you define the parameters. Okay, here we are. The answer to Grant's question, what is the basis of built-in soil properties used in integral bridge support menu? So it is based on Matlock and RESI, and this is how the PY curves are generated. It's a very standard approach that is generally used by geotechnical engineers to obtain the soil spring supports, and structural engineers also use this approach. And you can, this is how Midas Civil generates the spring supports when you use the integral bridge supports. Okay, so let me take on more questions here. There is a question from Jack. The question is, with a light superstructure and a heavy footing, it could be difficult to achieve 90% mass. What do you do then? Well, if it is difficult to achieve a 90% mass, then you can go ahead and do the analysis without taking into account the 90% mass. But then you have certain factors that you can apply to increase the effect of the load. So this is how you do it. But Jack, we can have a detailed discussion on it, because I'll have to dig into the code and see which clause talks about it. There is a question by Christian. The question is, what about the live loads? How does Midas consider into masses for response spectrum? Well, the live loads generally are, you can take into account 20% of the live load or 30% of the live load, depending on what the code says. And it's very easy. You just have to apply a factor of, you just have to apply additional load in the software, in the Midas software or any other software. Just define additional mass based on the live load, and then you can perform response spectrum analysis. So again, when you are talking about how to consider the live load while performing the response spectrum analysis, it's a whole new science again. You have to consider what would be the critical position of the vehicle and all. So it would be difficult to answer this question in a live session, but yes, we can have a detailed session on it anytime. Okay, there is a Benjamin. Hi, so Benjamin has replied to one of the queries here, and it says that the code does not apply live loading due to the ability of the suspension not to impact the bridge movements. So Christian, I think he has replied to your query. But yes, when you talk about the buildings, I was talking in a more general manner. if you have live loads in a building, then you take into account a certain percentage of the live load to consider the mass. And if you are designing the jetties and all, then it has to be considered. But I guess in live load, the suspension will take care of it. But yes, if you want to apply again, you can just add some of it to the self-weight of the structure and convert it into mass and perform analysis. So guys, if you have any more questions, I can reply to your questions right now. Otherwise, I'll hand it over to Daryl, and he will give you a final note on this particular session. So I would like to thank you from my side. Thanks for attending the session. I hope I could deliver myself effectively, and I hope you guys understood the different aspects that I talked about today. Please send me your remarks or feedback at ts@midasuser.com. Let me pull up the address once again. If you have any feedback on how we can improve our sessions, you can send us the feedback at ts@midasuser.com. And if you have any technical question, you can ask at this email address. So thanks a lot. I will hand over to Daryl now. Thanks a lot.
Okay, thank you, Nithil, for the presentation, and thank you all for attending. I hope you all enjoyed it. So just as a reminder, here's the schedule that we have for our upcoming seminars. Next week we'll have a discussion on the numerical modeling and analysis the numerical modeling and training and analysis training for displacement time history analysis of long-span bridges by Puya. And then next week on Friday the 28th, Deanna Nevling of Michael Baker will be giving a technical seminar on a steel I-girder bridge design. And then next month on the 2nd, Nithil will be speaking again, and he'll be giving the the numerical modeling and analysis training for response spectrum analysis. So for those of you who maybe want to see the recording of past seminars or the recording of this seminar, they will be available on goodengineers.com. You can also use this website to register for our upcoming seminars. And also, if you have any questions just about the webinars in general, you can send them to this email address. Okay, so thank you all again for coming, and I hope you all have a good weekend. Take care now.